Okay, so in this video we'll do question 5. So in question 5, you are asked to use the moment generating function to show that if Q has chi-square distribution of parameter nu, then the expectation of Q is equal to nu, and the variance of Q is equal to 2 nu. Okay. So let's just compute the moment generating function for the chi-square random variable, right? So let's see. Okay. So if Q is chi-square nu distributed, then the density function of Q is given by x nu on 2 minus 1 e minus x on 2, and you divide everything by 2 to the power nu on 2 gamma nu on 2 for x greater than 0. Okay. Of course, the quick way to do this is to recall that if Q is chi-square nu, then in fact this is a special case of gamma, and this tells me Q must be gamma with parameter nu on 2 and 2. Okay, but so this is nothing more than computing the moment generating function of the gamma random variable. But anyway, let's do this. Right. So you take integral from 0 to infinity, since the domain is from 0 to infinity. Then you take these constants. So let me just write these constants. Right, gamma nu on 2. Then you have to integrate against x nu on 2 minus 1 e to the power minus x on 2. But the moment generating function, of course, it's ux dx. Right, so that's the MGF. So this is the MGF of what? Q at u. Right. Okay, so we just have to compute this. All right, combine these two exponential terms, you'll get 2 mu on 2, 1 on gamma nu on 2, integral 0 to positive infinity, x nu on 2 minus 1. Then I have e to the power of, so what is this? You say this is gonna be minus a half minus u x dx. Okay, so once you get there, to proceed, make the substitution. So let's do a half minus u x is equal to, say, I don't know, y. Okay, I'll make this substitution. Okay, so let's move the paper up. Okay. So now once you make the substitution, of course, you write these constants out again. Okay. Infinity. Then, okay, since you have a half minus ux is equal to y, you just have to, of course, the limits doesn't change, right? When x is equal to 0, this is y is equal to 0. When x is equal to infinity, y is equal to infinity. The limit doesn't change. So you just have to replace x by some function of y. So this will be y to the nu on 2 minus 1. But then you gotta have a half minus u to the power of minus mu nu on 2 minus 1. And then for the part with the exponential, we have e minus y. And then dx is equal to a half minus nu to the power minus 1 dy. Okay, so we just have to compute this. Okay, so that's a constant. That's a constant. So you see that you have plus 1 and then minus 1 on an exponent. So this cancels out. So I should get. So I should get what, a half. Don't worry about that. Minus u to the power minus nu on 2, right? And then I'll have these constants. Gamma nu on 2, integral 0 to infinity y. This is nu on 2 minus 1 e to the minus y dy. Okay, so if you stare at this hard enough, you should see that this is the what? This is 1, because this is the density of a gamma, what is it? Nu on 2 and 1 random variable. Okay, so this is density of gamma nu on 2, 1 random variable. So that integrates to 1, and we'll have this, right? So this is so what is that? That is, of course, 1 minus 2u to the power of nu on 2, right? So there we go. That's the moment generating function of a chi-squared random variable with parameter nu. Okay, so let's put a little box, draw a smiley face, we're done. Okay. Oh yes, of course I have to say that what is it? U has to be smaller than a half, because or else the denominator explodes, right? Or you have a root of a negative number, which is not good. Okay. Right, so that's the moment generating function. So we're gonna use this to answer the question. Or you can just memorize the expectation and the variance of the gamma random variable, right? So mqu is equal to 1 minus 2u to the minus on nu on 2. Right, so the first derivative of the MGF with respect to u, this is equal to minus mu on 2, 1 minus 2u minus nu on 2 minus 1. You got to differentiate against u, so you have minus 2. So this is going to be nu multiplied by 1 minus 2u minus nu on 2 minus 1. But therefore, this tells me the moment generating function at u is equal to 0. This is simply equal. When you substitute u is equal to 0, this is 0, so you simply get nu. Okay. Great. Fine. Now, to compute the variance, we have to compute the second moment. Okay. So let me just finish off. Therefore, expectation of q is equal to nu. Right. For the variance of q, of course, this is equal to the expectation of q squared minus the expectation of q all squared. Right, we already worked that out, so we just have to work the second moment. But the second moment is to compute the second moment, you need to compute the second derivative of the MGF. So this is the first derivative. So we compute the second derivative. Of course, then you just differentiate this bit here. So I should get minus nu 2 plus 1 when I drop the exponent, and then I still have to keep this and then subtract another 1 off from that, minus 2, and then I have differentiate with respect to u in the middle. Right, so this is minus 2. So the minus is going to cancel off, so I get 2 nu on 2 plus 1, 1 minus 2u minus nu on 2 minus 2. Right, of course, now you see that the second derivative of the moment generating function at u is equal to 0. This is equal to, say, nu plus 2. Right, since when you substitute u is equal to 0 here, this will be 0. So let me just check whether I got this right. Let's have a look. Okay, not yet, since I forgot to subtract the expectation, right? So therefore, expectation of q squared, this is equal to nu squared plus 2 nu, right? This tells me the variance of q is equal to nu squared plus 2 nu minus nu squared, which is 2 nu. Right, so that's it. Good, tick tick. So, okay, so I've shown the variance of q is equal to 2 nu. Right, okay. Now, so we can move on to, say, question